everybody, I'm just going to go over the electrophilic aromatic substitution reactions that we talked about the other day. So for this, when we have just benzene as a starting material, it becomes fairly straightforward to determine what product you're going to be making, because you can pick anywhere on the ring and it'll be the same product. So we don't have any type of, any particular substitution patterns that we need to worry about. So I'm just going to briefly go through the reactions. I'm not going to do the mechanisms out because we kind of did them in class, but we're going to spend most of our time in this video talking about how to deal with substitution on the benzene and what kinds of strategies we can look for. So this first one, though, is a nitration reaction. So I'll just go ahead and label this. So this is our nitration, uses nitric acid and sulfuric acid. The next one with the sulfur, that's a sulfonation. You can use sulfur trioxide and sulfuric acid, or just concentrated sulfuric acid for that one. Then we have our halogenation. That one you can do it with chlorine or bromine, depending on what you want to do. For that, you really just need to make sure that you're adding in a Lewis acid in most cases. There are some instances where you don't need that if you've got a particular substitution already on your benzene ring, but for an unsubstituted benzene, you would need to have a Lewis acid to give it some more oomph. Next is going to be the Friedel-Crafts acylation. Okay, and the acylation is the one that gives you the ketone product. So we're starting off with an acid chloride as one of our reactants, adding in another Lewis acid, and then we get our ketone out. Okay, and then the other Friedel-Crafts option is the alkylation. So it's the difference between alkylation, where you're adding an alkyl group, acylation, you're adding an acyl group. Okay, so the important thing is for the Friedel-Crafts options, both of them, they have to have either a straight benzene ring or they have to be an activated benzene ring. So they do not work with a deactivated ring. That got away from me. Okay, so we have to have a pretty activated or, not unactivated benzene ring to enable it to be a good enough nucleophile to react with a little bit of a poor electrophile. So that's the only kind of caveat there with the Friedel-Crafts, is we need to have it activated or at least not deactivated. So if you're not sure about activated or deactivated yet, check out the other video. It goes through, what makes it a ring, activated or deactivated. Okay, so let's go through some examples with substituents on it. Okay, so let's just start off with so this is anisole, and we're going to do a Friedel-Crafts reaction with it. It's an electron donating group, right? So I've got the lone pairs right next to the ring. So it's going to be donating here, which means that that benzene ring is going to be activated and more nucleophilic than if I had an electron withdrawing group present. So we're going to go ahead and do a Friedel-Crafts acylation. And we're going to go through the mechanism and think about how we can predict what product is going to be our major product with this particular starting material. Okay, so if we start off with forming the electrophile, that's going to be the first step in most cases here. So we're going to go react with our Lewis acid. Okay, we can pop off that AlCl4. That gets us to our acylium ion. Oops. So the reason that this carbocation is so good is because it's actually resonance stabilized with the oxygen. So this is the major contributing resonance structure where we have all atoms having a full octet. And that's where our benzene is going to come in. Okay, so I'm going to list this out in the different substitutions that you can see. So we're going to start drawing out what the ortho position is going to look like. And once you get practiced at this, you don't have to do every single one every single time. I'm just kind of showing you how you can work through it if you need to. So we're going to go for the ortho position here. So we're going to attack our electrophile with one of the pi bonds. So we never want to be substituting on the same carbon as the substituent is already on, because at the end we need to be thinking about remaking benzene. So we have to put it somewhere where we have an H that we can get rid of, and then get this pi bond back. Okay, so we're going to make sure that this doesn't move. We put our new group over here. So then that means that our positive charge is on the carbon right next to the oxygen. So if we're starting off, when you're trying to determine what the substituent, like what kind of substitution pattern you're going to have based off of, whatever you have on your benzene ring, it all comes down to this carbocation intermediate. So how stable is it when I put something in the ortho position? Is it a good carbocation, or could I make a better one? The only way to find that out is to draw the resonance structures. So I'm going to start by recognizing that I've got lone pairs on that oxygen. So I can use that to help me stabilize that positive charge. Okay, so I have that option. That's a really good one because, again, I've got all atoms having a full octet here. So I could have moved this over. So I'm going to just do that in 2 steps to essentially go through this, and then we get to use that pi bond as well. To get us that carbocation, one more little resonance structure here. It's always hard to draw on the edge of the iPad. And then I get to that carbocation over there. So not a bad little range of delocalization, pretty nice. By the time we get over here, I pretty much don't have anything else that I can do. So that's when we're going to go straight for the reformation of the benzene using our AlCl4 as a base. So then I get to that product. Okay, so that's how I would get to the ortho product. To really determine whether that's a good thing or not, we need to do the rest. So let's go ahead and do the meta. And I'm gonna put it onto the next page because otherwise it'll be a mess. All right, we're gonna go a little bit faster on this one because we're gonna get more comfortable with those resonance structures. Okay, so for meta, we need to grab this alkene. We're going to put that ketone in the meta position. And our carbocation is going to be over here based on how I drew things. Alrighty, so then we are ready to go for our resonance. So I'm going to go straight for that pi bond because that's the only option I have at this point. Okay, and then the other pi bond. To get over here. So if you notice what happened, we skipped right over that atom. We can never put the positive charge on the atom next to the oxygen. So we are never able to take advantage of the fact that we have an oxygen there to help us stabilize that carbocation. Okay, so we skipped right over it. We cannot use it. By the time we get around to the other side, we've gotten all of the resonance structures that we can. So now we're ready to reform our benzene ring. And get to our meta product. Okay, let's go for para. So the beginning is still the same. It's actually identical to the meta. We're just going to choose the other side to put it on. So we're going to put it in the meta position, or goodness, in the para position from our methoxy group, which means our carbocation is going to be where on the meta of carbon. Okay, for resonance time. I've hit the magic sauce. So I've been able to get my carbocation on the carbon next to the oxygen. So I can take advantage of that. I'm going to draw out that resonance structure. Okay, so I have this one. We like it. That's a good one. I could have also used that other pi bond, so I'm going to go ahead and do that as well. Okay, so I can get to here. I've gotten all the way around the ring. Can't do much more. Time to remake my benzene. To get to my para product. Okay, so what we've got here, my resonance structures for the para are pretty much identical to the ones in the ortho position, right? So anything that puts it in the ortho or the para, those are going to be the same resonance structure. You're going to end up with the same carbocations for both of them in pretty much all cases. I don't think we're really going to talk about any cases where you don't, because they're a little outside of the scope of the class. So we have very nice resonance structures for both of them. And in both of them, we're able to take advantage of a full octet resonance structure, right? So one there and this one here. Okay, so the ortho and the para have a little step up, a little leg up over the meta product, where it has pretty decent stabilization. Like, you know, in terms of carbocation land, it's pretty stable because it's got a lot of resonance, but it doesn't have as much as the ortho and para. So it's not as much or as good resonance as ortho and para products. Okay, so our meta is going to be the minor product. The para is going to be the major, shared with the ortho. Okay, oftentimes you'll see para be a little bit major, like just over the ortho in general, because we have our groups spread out. So you can imagine in the ortho, if we start to see any kind of like steric repulsion, it's just going to be easier for it to approach from the para, or sorry, from the para position. Oh no, that I was right the first time. From the para position, just to avoid any steric interactions. But you're going to end up seeing ortho and para in most cases. But there are things that you can do to kind of rig the game a little bit. Okay, so now let's talk about what happens. So this was a case of electron withdrawing. So let's just go ahead and finish this up. Or this was electron donating. Goodness. Okay, so we get the ortho and our para. Okay, so those are our major products with an electron donating group. Okay, so electron donating, ortho, para. Let's see what happens if we do electron withdrawing. Okay, let's look at what happens when we've got a nitrile involved. Okay. And let's go ahead and do a nitration reaction. Okay, so same thing, we're going to do the electrophile formation first, and then followed by ortho-meta-para options. Okay, so we've got nitric acid first. With sulfuric acid, really lovely mixture. We're going to protonate our nitric acid. That's going to make a good leaving group in the form of water, where we can bring down another oxygen lone pair, kick off our water, and form our NO2 plus. Okay. All right, so now we're ready to go through our ortho-meta-para products. All right, let's start with the ortho just like we did last time. Okay, so we're gonna go right for that nitrogen and kick electrons up. So it's just like when we did the Friedel-Crafts one up above, where we attacked the carbon and then moved electrons up onto the oxygen. Very similar process here. Just think about that kind of like that carbonyl bit. Okay. Same deal here. We're not going to be putting anything anything on the same carbon as the substituent is on. Okay, so I've got a positive charge right here. So one thing that we want to keep in mind is we do need to think about the resonance structures involving our nitrile in this case. So again, just like in a carbonyl, I cannot do that because that's going to take electrons away from my nitrogen, which is electronegative. So the only option that I can do is actually this way, away from the positive charge. So that I end up with that, which is hideous. It's just terrible. Okay, so the really big problem here is that I've got two delta plus carbons right next to each other. It's not like it's a delta plus next to a delta plus on an O or something like that. It is two carbons right next to each other. So they really can't do anything about that. So that's not great. We're just going to put a little sad face there. All right. So we have that little sad resonance structure there. We don't like it, but it does exist. And then let's keep on going with the other resonance structures that we have. Okay, and then we can do one more. Here, okay? By that point, I am at the end of the line. And so now we can go ahead and bring in our base. So in this case, so since I don't have any, the only thing that I made was water. So we're going to use water as a base in this one. We're going to reform our benzene. To get to our ortho product. Okay, so that's the ortho. Let's look at the meta. Okay, so same attack. We get to our carbocation intermediate. Put it in the meta position this time because that's what we decided to do. I'm just going to go ahead and draw it out too. Okay, so we got our positive charge here. Let's go ahead and do our resonance. Okay, so we have that one. We skip over, use the other pi bond. Positive charge, nitro group, and we've pretty much hit the end. So again, just like we saw in the example above, where we were talking about the electron donating groups, we saw that the meta position skips over with putting the charge on the atom that has the substituent on it. In this case, that's actually a very, very good thing, right? Because that avoids this entire situation where you've got two delta positive carbons right next to each other. In this case, we have our delta positive carbons nicely spread out. So they're never really coming into close contact with the delta plus carbon of our nitrile. Okay, so this is kind of a good thing that we're avoiding that situation. So at that point, I don't have any other resonance structures to draw out. And we've got our water coming in, making that pi bond. And we get our final meta product. Okay, let's look at what happens if we do para. Hopefully you're starting to see the pattern that it won't be very different than what we've seen already. All right, para time. Resonance. Okay, so I'm starting to get a little worried here. I've got my positive charge where I did not want it, right? Because I still have a delta plus on that carbon, right? You don't necessarily have to draw the resonance structure to show it, but it is there. There is no getting away the fact that this carbon is delta plus. Okay, sometimes I just like to draw the resonance structure out to see it with my eyes. It is obviously not a super like major contributing resonance structure because I am making charges, but it's still present. So it's still part of the overall picture here. Okay, so we are still unhappy about that. We're gonna mark that with another sad face. Okay, and then we can keep on going around the ring. So we can go, I'm gonna start from this guy. And I can go back to going around the ring. So then I get to the end, I can use my water to come in here, grab that H. And get to my para product. Okay, so both the ortho and the para put 2 delta plus carbons right next to each other. Not good. Okay, the meta avoids that problem. Okay, so we've got minor for the para, minor for the ortho, major for the meta. Okay, so electron withdrawing groups, meta. Okay, just to avoid having that delta plus right next to the delta plus for the carbons. Okay, the other way that you can kind of think about this is you can actually start from the starting structure. So this, all of these is really why it is choosing a certain substitution. But the other way to kind of think about it is by looking at what carbons are either nucleophilic or not nucleophilic in the starting material. Okay, so let's just take, for example, the first one. With our anisole here. Okay, so we kind of talked a little bit about how we had this resonance structure using the lone pairs. So that resonance structure still exists even if there's not a carbocation in there, right? We can push the lone pairs into the ring. That's what makes it a donating group. And we can look at where those electrons fall. Okay, so I can put a negative charge here in the ortho position. I can also put it in the para position. And we can loop around to the other ortho position and see it there. Okay, so if we look at the hybrid here, we've got electrons delocalized through the ring, right? That's typical of benzene. But then we also have, so this oxygen is delta plus, and then we've got delta minus, delta minus, delta minus on our ortho and para positions. Okay, so the ortho and para positions are more nucleophilic than the meta. Okay, if we look at the other starting material we used with the nitrile present, okay, again, we have to think about what direction is the electron, are the electrons flowing, and it's towards the nitrogen, right? Towards the electronegative atom that's attached. So we're going to start out by making that carbon positively charged. Okay, so we have a positive charge. We can push electrons towards that. And this looks a little bit funky with a nitrile, but it's the same concept with a carbonyl or anything like that. It's just not going to look quite so weird and SP shaped. Okay, but we're going to have a positive charge right there. You're going to delocalize that around the ring, see where it ends up. And one more time. To get here. Okay, so if we look at the hybrid on this one, what we scattered through the benzene ring is not negative charges this time. It is positive. Okay, so our nitrogen had a delta minus, carbon had a delta plus, and then we had delta plus, delta plus, delta plus. Okay, so we actually have our charges falling in the same places as in the electron donating group case, but they are just opposite charges. Okay, so now these carbons are less nucleophilic than the ones that don't have any charges on it, because at least they're not positive. So a nucleophile that's positively charged is not going to be a very good nucleophile. Okay, so the meta positions here are more nucleophilic. Because they don't have a delta positive. Okay, so just think about, you can think about it in a variety of different ways, like what's going to stabilize the carbocation the best, or think about it in terms of from the beginning, you know, where would I predict the substitution to occur? Both of them are valid options. I would say in terms of like, if you're asked about rate or something, it's going to have to do with the intermediate itself. But predicting the product is going to be helpful to kind of think about it in this way. Alrighty, so I know these are kind of long. Let me know if you have any questions, and we will keep talking about this stuff.